Hey, go ahead and say hello so I know who's there. I see 3, 4 of you. That would be swell. Good morning. Welcome to my basement or studio, if you like that word better. So hopefully you can hear me okay and see me okay. I look a little pixely to myself, so I hope you can see the whiteboard because that's what we're going to use this morning. I'll get this sucker as close as I can to the whiteboard. Ah. Like that. Let's get that out of the way. Okay. Just say hello so I know you're there and I know who's there. And then we get a few more of you, then we'll get started. We're going to go from 8 till 9:30 today. Strange, I can't see this. If you're typing, I can't see anything. That's really weird. I got 5 of you, but I'm not seeing the chat. I wonder what's up. Oh, there's one. Okay, Shilpa's there. Good morning. Okay, so Shilpa, can you see and hear me okay? In fact, I'm going to write something on this. Let me know if you can see the whiteboard okay. You can see the others said on the WhatsApp chat that they cannot comment though. That is so weird. I wonder why not. Okay. Well, hi everybody. I'm sorry you can't comment because that's kind of part of the deal. Oh my. All right, I'll go to the WhatsApp and let's just comment on here, okay? Seems silly, but I guess I'll use two you know, technologies at once here. Okay, good. Okay, so everybody's there. Gosh almighty, I love it. So good morning, Sarah, Rhea, Aaron, Lena, Shilpa, Leah, and Quinn. Okay. And for all of you, I will record this, so any of the examples that I do, you can look back and see from the recording, I hope. Okay? All right, so let's begin. First off, to you, are there any problems in chapter 2 you'd like to see worked out or you'd like to ask about? So type in here on the WhatsApp if you can't do it on the live chat. I don't know why that would be not allowing you. Oh, there's one already. Okay. Thanks. Aaron's suggestion. So we'll do page 108, number 3. Off we go. Okay, let's have a look at it. Others, you can type in some other ones. We'll get to them all. Now put that down there. Make sure I read it right. Okay, this is a internal heat problem. So a system releases 64 kilojoules of energy. Okay, releases 64 kilojoules as its internal energy is increased by 43. Internal increased by 43. Did the system do work on the surroundings, or was work done on the system? How much work was involved? Okay, so the system released 64 kilojoules of energy. So we're going to just think, okay, so energy is, well, it's heat, it's Q plus the work. So let's just figure out which is which, okay? You guys could type in if you got some help to offer. Okay, a system releases energy as its internal energy is increased by 43. Oh, Lord, Cheryl. I wish you could just use the word heat. Okay, we're supposed to figure out the work. So work will be our variable, and we got to figure out which one of these goes where and what sign it will have. So a system releases 64 kilojoules. So if it releases it, it's going to be, yeah, I'm sure you're saying it. It's going to be negative because you're all smart. So let's see what the other one says. Its internal energy is increased by 43. Is increased by 43. The wording's very poor, Aaron. Let's just see if I can figure it out. The system releases 64. I'm guessing Q is negative 64 kilojoules. Let's see if this works out. Okay, equals, and its internal energy is increased by 43. Internal energy increased. So maybe that's positive. If that's the case, then our work's going to be some big positive number. They don't even want to know how much, do they? Yeah, they do want to know how much. Okay, so it would be 64 and 43 would be plus what, 107? And I could be wrong about this, folks. If I'm wrong about the signs, so be it. Okay, but that's my guess as to what they're talking about. And again, the word, it's not worded very well. It would be worded more clearly on the AP. Okay, let's answer the questions. Did the system do work on the surroundings, or was work done on the system? Okay, how much work was involved? Well, we got the work, at least if I'm right, 107 kilojoules, and it's positive, so work is done on the what? So positive, so work done by the surroundings on the system. Remember, if it's negative, then it's from the system pushing out to the surroundings. So it's got to be, if it's positive, the work's done by the surroundings on the system. Okay, that's my best guess for that one, Aaron. Let's see if I'll pick up my phone. Let's see if I got another suggestion from all of you. And I hope that's the answer the book got, but you know, if it's not, it's in the wording. Okie dokie. and we got another one. So from Rhea, we got the next page, page 109. Oh, and I see from Aaron, number 2 is a question as well. Number 2 should be a lot more straightforward. I'll tell you what, we'll do number 2, Rhea, and then we'll do number 2, Aaron, and then Rhea will do number 1 on the next page for you. Okay, so first let's do number 2. Thank God we got that WhatsApp group, or else this would not be working. Okay, and let me know if there's a color or something that doesn't show up. Let's try the red for grins here. 2, it's not my brightest red. Okay, a system, well, let's do our equation. So energy is Q plus W. And number 2 says, page 108, a system releases 475 joules of heat as it performs 524 joules on the surroundings. Okay, it releases heat, so that's going to be negative. So negative 475. And it performs, right, pushing out against the surroundings. So that's going to be negative 524 if I am right here. So plus and negative 524. Those are both kilojoules. No, they're not. They're joules. J. Okay. So the energy is going to be equal to a really big negative number. So negative 999. Is that right? Are they getting cute on us with a number like that? 999. Duh. So negative 999 joules. I think that's it. Okay, so there we go. Okay, let's go to the next page. And for Ray, we're going to look at page 109. And I think, Ray, you said number 1. But with my short-term memory as it is, oh, she meant number 2 on 109. Good thing I looked. Okay, so number 2, page 109. Here we go. Maybe I'll go back to blue. That seems to show up better. So page 109, number 2. Says we've got a cylinder equipped with a piston. I love it. Some good physics in there. Piston expands against an internal pressure of 1.04 atmospheres. A combusted fuel causes an expansion from 0.243 liters to 1. Oh, I got to write some of this down. With the emission of blah blah heat. What's delta E for the process? Be sure to include the conversion factor 101.3 joules per liter atmosphere where necessary. Holy moly. Okay, so we need that equation that is this one. It's right up in the example above that on page 109. So our equation, I think, is going to be this. W, change in E. Is that what they want? Yeah. Ah, God, I said E and I wrote H. Damn it. Okay, change in E equals delta H minus delta N RT. No, we can't use that one. we can't use that one. It's going to be minus delta P. No, it's not. It's minus P times delta V. Okay, here we go. All right, let's maybe, well, okay, we'll try and do the whole thing in here. They gave us a conversion factor, so so that should work out. Okay, so we've got okay, we're emitting 1.553 kilojoules of heat. So I'm going to put this as, now the other stuff's going to come out in regular joules. So I'm going to do this as delta H is a minus 1553, so 1,553 joules. Minus, okay, then we got a pressure of 1.04 atmospheres times the change in volume. So it's going to be final minus initial, I think. So it's going to be 1.650 liters minus 0.243, 0.243 liters. Okay, then we also got to multiply by that conversion factor. So here we go. Be sure to include the conversion factor, blah, 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 joules per liter atmosphere. Okay, so we got to multiply that times 101.3 joules per liter atmosphere. So times, sorry to run out of space, oh Lord, that's too small. You can't see that. Times 101.3 joules per liter atmosphere. Okay, this is one where I would advise putting all the labels in just to keep yourself honest. So you can get things like the conversion factor and make sure it's all in regular joules. Otherwise, you know what. Okay, so everybody want to punch that out, and I will too. Why don't you type in what you get? See if you get the same thing as me. Pardon me. So we got 1.65 minus 0.243 equals times 1.04 equals times 101.3 equals. Okay, so I get 148 for all that. So plus a negative 1,553 equals. Okay, I got minus, oh, this is a German calculator, damn it. I think I got minus 1405 joules. See if others get the same thing. Let me know if I got the same thing as the book. Doing my best here in the basement. Good thing I charged my phone, huh? Okay, how'd we do there? Okay, Ray, did that help? Is that okay? And Aaron, did that help for your other ones? And is that okay? And I'm open for other questions from any of you now as well. So type in, or Shilpa, if you've got one, just type it into the chat. I don't know why the others can't chat. I'm going to look here at the menu and see if I can figure it out. Hey, so Noah Delphs is on there. And he's got a suggestion. Page 109, number 1. That's a popular page, page 109. Okay, we'll do that, Noah, in just a second. Let me see if you're over here. Yeah, you're there too. Okay, I'll just leave it there then. Okay, let me see if anybody else is typing in here to give me a message as per how that went. Okay, so Aaron says, I guess, that it should have been, and I'm guessing you mean this one, Aaron, it should be negative 1.70 kilojoules per mole per the answer key. Unless you can find my error, I'm guessing the book is wrong. If you can find my error, please say so, okay? So feel free to check, and just like in the classroom, tell me where I did something wrong, but I think that's the way we got to do that one. We did the pressure times the change in volume. Our labels are correct. We've got a conversion to get it back to joules. And even if I make that negative, well, let's see. Let me read it. Okay, so okay, wait a minute. I think I found my mistake. Hold on. So I'm still looking at number 2 on page 109. And it causes an expansion. And if it causes an expansion, yeah, it's exerting pressure. So if it's causing an expansion, maybe I need to make this positive. No, that's not working. Wait a minute. I did something wrong here. This should be more negative. Yeah, it's an explosive expansion. I agree, Quinn. So it should be more negative. So I screwed up my math somehow. Okay, so this is positive, 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 and there's a negative in there. That's what I screwed up on. Okay, so it should be, that should be that I got to do it all over again. All right, I just didn't put in this negative sign. So start again, Mr. Weiss. Here we go, 1.04. It's so hard to get help anymore. No, we're not going to start with that. I'm going to subtract these two first. 1.65 minus 0.243 equals, okay, so times 1.04 times 101.3 equals, okay, so it's negative 148 plus this. So negative 148 joules. Okay, so that's negative. Oh, Lord. Okay. Okay, so then we're going to go minus 15. Okay, guess what, Aaron? If we do that, and I remember my minus sign, that's my problem right there. We get the right answer, by golly. So negative 1.701. I don't know how they're running for sig figs. I don't care right now. But thanks everybody for the help. And yes, that was the mistake. I forgot my minus sign. So it does come out to the right answer, Aaron. Okay, let's go on to page 109, number 1. That from Noah. Okay, so that's right, 109, number 1. Okay, so here we go. Hope everybody's got that down. I'm going to erase it because it looks like hell anyway. And let's try number 1. Again, this will be on video, so you'll be able to look stuff up, okay? Okay, here we go. Consider the imaginary reaction. A plus a couple of B's, something, C somethings, forms 4 D's and 3 E, F somethings. The reaction's E value, energy, is measured at 442.26 kilojoules per mole. What is delta H? Okay, so we've got to be able to get the okay. Everybody look carefully carefully at that problem. See how the very end it says delta H with a little circle? That means 1 atmosphere, 25 degrees C. Okay, so that may be helpful. All right, so let's think back about work. And remember, work can be the pressure, change in volume, and we don't have anything with change in volume. That's the one we just did with Aaron. That's the one we have number 2. But I do got a change in moles of gas. So we're going to do negative change in number of moles of gas times RT. Okay? So let's do that to get the work. And we already have E. E is 442.26. 442.26 kilojoules per mole. Okay. All right, so let's get this puppy. Okay, so bum, 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 bum. Okay, change in moles of gas. Remember, it's moles of product minus moles of reactants, gases. So let's just count it up together. Oh man, I put my glasses on here. So I got 3 moles there. I got 4 moles. Are we looking like 7 moles of gas on the product side? Does that sound right? Minus, well, freaking hey, I got an aqueous and I got a solid. That's not very much. So it's looking like 7. Yep, I think that's it. So I got 7 moles times the R is 8.31 joules per mole Kelvin. I know it's because I've been here forever. I know that one. That would be given on the AP, by the way. And the temperature, because they got a little circle on the delta H, it's 25 degrees C, so 298 Kelvin. And once we get that, we can solve for, I'm going to let you finish this one up, I think. So it's going to be negative something or other. And then to get delta H, it'll be, oh man, it'll be work minus the energy. Okay? Did I do that right? I think so. I hope so. And delta H is basically Q. Okay? Don't let them, they're getting cute about this whole thing. Sorry. Okay, so Q or delta H is, yeah, the work minus, no, it's not. God, it's because it's early in the morning, isn't it? So if that's Q and I'm solving for that, get with it, teacher. It's going to be delta E minus minus the work. Does that look right now? Okay, and don't forget your work's going to be negative, so it's going to become positive here. So watch your signs, but it should come out right. Okay, the rest I think you can finish up on that. I hope that was helpful. Aaron, I think you asked for that one, or was it Rhea? Let's see what other ones you guys want to ask about. That's a calculator. That's a phone. Okay, so here we go. Okay, so glancing down here, I think we got all of them so far. Any last questions you want to ask about? Oh, that was from Noah D. So I hope Noah D, that was helpful for you to have enough now to finish up. Okay, got another one from Noah D, and it's page 119, number 1. So here I go. Turning low. Oh, that's a nice one, isn't it? Okay, so page 119, number 1. Enthalpy changes from average bond energy values. Okay, so we got to use the data at the back of the book, probably. Or in the book, maybe it's in the book. Table 2.2.2.2. Okay, probably in the book, to produce a full thermochemical equation for each of the molecular representations below. All right. I'm going to set this here. That doesn't disturb you guys. Okay, so let's start again here. So page, we'll go back to blue. Old blue. Page 119. Oh, that's black. Number 1. Let me make sure that's it. Yeah. Okay. Good. Okay, so page 222. There it is. There it is. Okay, so full thermochemical equation for each of the molecular representations below. All right, here we go. I'm assuming, Noah, that based on the picture on page 117, the first chemical is H2. So I'm just going to write it that way, okay? H2 plus. Now the second one, we got to figure out what the heck that one is. Look at the size of the spheres. I'm guessing it's Cl2 because it doesn't look big enough for a Br. Let's call it that, Cl2, okay? Makes 2 HCl. Is that what others got too? Thank you. Okay. Is that what others got too for this one? Did you call it H2 plus Cl2 makes 2 HCl? Okay, so a full thermochemical equation. All right, so what does she want? Well, we need the delta. We need the change in heat. So first let's get the change in heat. So it's the bonds broken minus the bonds formed. Bonds broken minus bonds formed. Okay, we're breaking an H2 and a Cl2, so let's just look those up. So H to H is 432, and it's in kilojoules per mole. And I'm breaking a Cl2. That's looking like, come on, puppy, where are you? There it is, 243. So 432 and 243 kilojoules minus the bonds formed. Well, I got two HCl's. There it is, 427 kilojoules. Okay, let me punch that out, and you can too. See if you get the same delta H I do. You're probably going to be way faster than me. Where'd I put that calculator? And I feel inept in this studio. 2. You think it's F2? Is that what they said in the book, Noah? Let's see. Because it's not big enough for Cl2? I gotta say, that's fairly crappy. On the AP, on the AP test, it would not matter. Well, if it's F2, then we'll just use the bonds for that. Let me see if others have a little something to say there too. If it really is, I'll change it in a second. Hold on. Okay, so we're unsure. Okay, all right. So maybe it is Cl2. I'll leave it the way it is. If it doesn't come out, Noah, that's life, and we'll have to fix it. Okay, so delta H equals 427. Okay, 2 times negative 427 equals plus 432 plus 243. That does not look right. 800, 600. That does not look right. Let's do it again. God darn it. 427 times 2. Okay, plus 432 plus 243. All right, this time I got negative 179 kilojoules. And let's read the question. Okay, thank you, Shopa. You got the same thing I did. Makes me a little more rested assured, okay? Thank you for punching that in. Everybody do that from now on. It's great. Okay, so they want a full thermochemical equation. So which one was that? I think that's the one where we got to put it in there, don't we? So it's going to be blah plus blah plus blah plus 179 kilojoules per mole. I think that's it. Isn't that a full thermochemical equation? I believe so, because we put it on the product side, right? Hoping that's what they want. Yeah? Good. And yeah, I'm glad you got lots of questions today. That tells me you're working hard on them. Thank you for your hard work. And let me know if you got other questions now. I'm going to check in here as well. And I'm going to blow my nose in a moment. Okay, so let's see. Thank you, Rhea. Okay, so that works out good. Okay, Aaron has a suggestion. 129, number 1. So let's do it. 129, calculation of heat changes. Oh, this is kind of good. Okay, this is like a lab we did in 10th grade, Aaron. I can't remember if I had you in 10th grade or not. But if I did, then we did this lab. If not, then you didn't. Let's see if others can remember how to do it. Quinn might have had this at his school. We'll see. Okay, so shut up, Mr. Weiss. Write the problem. 129, number 1. I'm going to stick with blue because that's the one working the best today. Hope you can see that okay. And yes, we're going to blow our nose. Hold on. Okie dokie. Think I'm ready now. Aluminum metal is commonly used to determine the temperature of different portions of a Bunsen burner. Calculate the heat required to completely melt a 0.325 gram piece of aluminum wire beginning at room temperature at 22.5 degrees. The melting point of aluminum is 660.3. So they're heated up to that. And its heat of fusion is 398 joules per gram. That means to physically melt the stuff. So heat of fusion. 398 joules per gram. Refer to this table, blah, 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 for the specific heat capacity. Okay, I hope they give us that nicely. Okay, the C value is 0.90. I thought it was 0.2. Okay, so the C, 0.90 joules per gram degree C. That's the C for aluminum. Okay, so, all right, the heat's going to be in 2 parts, and it goes like this, Aaron. So to get the heat, I got to go, it's the heat to warm it up, heat to warm, plus the heat to melt. Well, the melting heat is this one, 398 joules per gram. So we just got to multiply that times 0.325 grams. We could do that over here in the problem, okay? The heat to the heat to warm the sucker is from this equation. It's Q equals mc delta T. So we're going to do the whole thing in here. You ready? So the heat equals, and I'll try and watch my labels. It's going to be the mass, M, so 0.325 grams, times the C value, I just looked that up, 0.90 joules per gram degree C, times the change in temperature. Okay, that's this whole thing. Golly, 660, because that's the final. 0.3 minus 22.5 degrees C. Okay, plus, just goes on and on, doesn't it? This is where I need your calculator and not this little stinky thing I got. Plus the mass, 0.325 grams, times the heat per gram, 398 joules per gram. Voila. I think I'm going to let you crank it out, folks, but I'm pretty sure that's the way to do it. So, philosophically, Aaron, it kind of goes like this. This sort of problem, you got to warm the sucker up, then you got to melt it once you get to the melting point. So it's 2 different types of calculation. One is the amount of heat to warm it. That's Q equals mc delta T. The other is the melting requirement, and that's the melting, heat of melting times the grams I've got to melt. So put those 2 together. Life should be good for number 1 on page 129. I think I'll let you finish up the rest of that. Okay, and I got a suggestion, looks like from Noah D. I'm going to turn to that. And Noah's asking about what is the heat of fusion? Okay, hold on. Question here. Heat of fusion is, let's say I got a chunk of solid, Noah, and it's literally the heat to break the atoms apart to make it into a liquid. So fusion is actually to bring things together, okay? But the same value numerically is used to break it apart. When I was your age, they call it the heat of melting, okay? Now they've decided to call it by the opposite name, fusion. So sorry about the confusion, but it's the same as the heat of melting. So the heat required to melt it is this much. It's also the heat given off if it goes from a liquid to a solid. I hope that helps. Okay, so I think Noah D, we're going to look at your problem now, which is the warm up on page 125. And we got an apparatus here to collect data. The hot plate supplies kinetic energy, of course. And as heat's absorbed, the temperature rises. And I got crushed ice. What is that energy being used for in each of the labeled regions on the graph? I love it. Okay. Approximately how much energy was used for each change to the water temperature. Okay, so I'm just going to write this down. Noah, can I ask you a question about this warm-up problem on page 125? Noah, is it the whole thing? If so, I'll start at the top, or is it just parts like 2 or 3 down at the bottom? There's like the chart, and then there's a question, and there's a question. I'm happy to do the whole thing, but just wondering if that's something you need or not. In the meantime, I'm going to make a little board space. Maybe if you type in an answer there. So page 125, the warm-up. Just 2 and 3. Thank you, Noah. Okay, so everybody, let's go down to it says study regions A, C, and E. What 3 things might cause the energy required to differ? Okay, A, C, E. Okay, A is we're warming up a solid. C is we're warming up a liquid. And E, we're warming steam, essentially, or gas. Okay, what three things might cause the energy required to differ? I'm not sure what they're asking for, but let's give it a crack. Unless if somebody looked it up, enlighten us. But I'll try and just do it thinking about it. Well, one thing that's different here, we'll list them 1, 2, 3. Well, the energy required, because the energy is doing different things. Here I'm warming a solid, here a liquid, here a gas. For the liquid, I'm warming atoms that can move around each other. So in addition to the vibration, that's a solid. Now I have physical movement around each other. So I'm going to say style of movement. So we got vibration, That's for a solid. We got just motion for liquid. And then we got a motion in air, a motion mixing with other gases. Probably. Or at least it's motion of particles that are far apart. And I don't know if she wants that as three things or if that's all one thing. Particles in gas are far apart. And I think that really changes how they absorb energy. So this is all about absorbing energy. What three things might cause the energy required to differ? I don't know if she's getting at what errors might be possible. Like for the first two, you're still in the beaker, so you might have heat absorbed by the beaker. For the third one, presumably it goes out into the air, so now you've got it mixing with the air. There's all sorts of errors, as it were. Yes, Quinn, that was a bad pun. Sorry about that. Beyond that, I don't really understand what she wants. But there's the main thing that comes to my mind is the style of the movement. Let's look at the last question too. It says study regions B and D. Okay, so we're melting and then we're vaporizing. What two things might cause the energy required to differ? Well, we're doing different things. Okay, so for B, I'll go here to the last one. 1, 2. For region B, we're melting it. So all we're doing is we're allowing solid particles to now move around each other. But for D, we're now pulling the particles of liquid apart and separating by a very wide distance. Maybe that's what she wants. That might be it. No, I think she wants those three things that I talked about, style of movement, as three separate items for 1, 2, and 3. And then for this last thing, what two things might cause the energy to differ? And I'm going to say the first one is for solid to liquid, particles free to move around each other. But for number two, I'd say we really got to say for liquid to gas, the particles are pulled widely apart. So pulled apart and far from each other, maybe we could say. And that's very different. It's a very different amount of energy because I'm doing such a different thing in two compared to one. Right? It's like you in a swimming pool with a bunch of people. For one, I just let you move around each other. For two, man, I pull you apart and like throw you out of the swimming pool and throw you far away. I think that's what they're getting at. I hope so, Noah. And I hope that was helpful. Let's see if I got comments from others and or any insights. You can certainly type in your insights, everybody. Good luck with that, Quinn. Okay. Oh my. Especially first thing in the morning. Okay. Any other questions from you? Is that one from Aaron? Let's see. Did we do that one yet, Aaron? Page 129. Yeah, that's the one we just did. Okay, so Lena has a suggestion. Is the screen blurry? I'm sorry if it is. I'm trying to get as close as I can here. Let me see if I can move the box even closer, Shopa. I think I'm a little pixely. Maybe that'll help. I just want you to be able to read that thing. Hope you can. Okay. Sorry, Sarah. Sorry, everybody. I don't know what I can do about the pixeliness. Okay, and I just lost that. So, doggone this phone. Okay, page from Lena, 122. And let's look at number 12. Okay, and then we'll get to Aaron's next suggestion in a second. All right, let's get rid of this. Maybe in blue it'll be less pixely looking. I hope you can see it better in blue. Blue seems to be my darkest marker here. Okay, so here we go, Lena. We got page 122. Number 12. Okay, it's another one with little models. That's okay. Consider the following unbalanced molecular representation of an oxidation reduction reaction. Translate the molecular representation to balanced formula equation. Then use the table of standard enthalpy of formation values from table 221 to determine overall enthalpy change for the balanced molecular equation. Okay, so it looks like we got N and O. So we got NO3. No, we got N2O5. Plus NO makes NO2. Okay, well, let's just take a crack at it here. Can I do 3 of these things? How many N's do I got? 3? Does that do it? So I got 1, 2, 3 N's, 3 N's. I got 6 O's, I got 6 O's. So that works out. Okay, so let's do that. Okay, so that's your reaction, I think, Lena. Now let's dink around with it. And I got to remember what they want me to do here for this sort of problem. So we're going to get the enthalpy change based on heats of formation. So 2, 2, 1. Let's find that. There's 2, 2, 2. Okay, there's table 2, 2, 1. So I think we're going to go products minus reactants. Yep. So we're going to do delta H equals H of products minus H of the reactants. Okay? Here we go. My products, I got 3 of these puppies and they're NO2s. So I got the, from table 221, NO2 is 33.2 kilojoules per mole. And I got 3 moles, so that's cool. Okay, minus, and now I'm going to put it in brackets. I got an N2O5, and that's 11.0. Plus, I got a NO. Oh, come on, Sherry. Where's the NO? Am I blind or is there not one in there, Lena? There's NO, 90.3. And then put that in brackets. I think, Lena, that's it. Let me look at 20, look at 12 again and see. Okay, does that, okay, Lena, does that help? I think that's enough to get you there. I'll let you crunch it out, but I'm pretty sure that's what we got to do. Great. So I'll let you do that. Let's go on to then another one and we'll get you started here. Aaron had another one to ask about, so let's see what that was. This chapter is difficult despite being short. Well, that's why I'm here, so I'm happy to help you out on these and get you on the right track. Some of it's just used to getting you used to know thinking about the processes and using these new little equations for work and energy and stuff like that. It's kind of a combination of physics with chemistry, isn't it? Okay, so I think we got Lena's. Let's now hit Aaron's, page 133, number 1. Page 133, number 1. Okay, let's have a look. I got 500 milliliters of 2 molar barium nitrate at some temperature is in a coffee cup calorimeter with 500 milliliters of 2 molar sodium sulfate. Okay, and you know what precipitate we're going to get. A white precipitate forms and the temperature of the mixture rises to blah blah. Assume the calorimeter materials absorb only a negligible quantity of heat and the final solution's density and specific heat capacity are identical to those of water. Thank you. So we don't have to look for that. Calculate the molar enthalpy of precipitation for barium sulfate. Okay, so molar enthalpy of precipitation. Okay, what are all these going to be? Molar, whatever is going to be kilojoules per mole. So we got to get two things. We got to get the kilojoules, we got to get the moles, and then we got to divide them. So 3 parts of the problem. Let's do the let's do the heat part. Okay, let's do the heat part first. So Q equals MC delta T. And we're going to use the mass, how much mass we got, right? 500 milliliters, and we got 500 milliliters. So we got 1,000 milliliters, so 1,000 grams. Remember, water 1 milliliter weighs 1 gram. So I got 1,000 milliliters, I got 1,000 grams. Times the C for water, 4.2 joules per gram degree C. You can use 4.18, I don't really care, times the change in temperature. So 25.6 minus 22.5. Okay, so let's get that. $25.6 minus 22.5. Okay, then times 4.2 times 1,000. Okay, I got 13,000. So let's make it 13. 13.02 kilojoules. See if you get the same thing. I hope you do. Okay, we're a third of the way there. Now we got to get the amount of moles. Okay, we can probably do this mentally. You see how everybody, they gave us nice numbers? Look at this. 500 milliliters is what? Half a liter. So I could do 0.5 times 2, so that'd be 1 mole of barium. By the way, did you figure out our precipitate is barium sulfate? So I got to figure out how much barium and how much sulfate and see if I run out of one or the other. Yeah, it may not be a nice equal equation. Let's find out. Okay, so I guess I should write some of this. I don't want to screw you up here. Let's do a little bit of writing. I can get rid of that. Okay, so moles of Ba2 plus. So 0.5 liters times 2 moles per liter equals 1 mole Ba2 plus. That's nice, okay? Then the other one is 500 milliliters of 2 molar sodium sulfate. We don't care about the sodium, but the sulfate is right. And you know what's the same numbers, isn't it? It's 500 times 2 molar, which also equals the moles of sulfate. So, gang, this is for 1 mole. So divided by 1 mole, barium sulfate, done. How nice is that? So in question 1, they were being kind of nice to you. They gave you for 1 mole of barium sulfate, the amount of energy. So that's already the molar enthalpy of precipitation. Okay? I think that's it. Good. So let's see what else you got here. I'll look on my screen and I'll look on the class chat. Okay, so it's 9:08 and everybody, I'd like to go till 9:30, so stretch a little bit as you need to. And at 9:30, we'll just call it quits, boop, because I got to go to conferences then anyway. But I'd like to introduce you. Actually, you know what I wanted to do is I wanted to do a couple more problems with you with ice tables. So let's do a couple of these together. We can't do as many as I wanted because you had a lot of questions, which is a good thing. But let's do these in our books. Okay, so I invite you to do these as I'm going to in my book. And here we go. So we're going to flip to the end of chapter 3. And I'm going to give you a page number. You can do these right in your book, okay? Okay, let's do a little warm up. So this should be relatively easy for you. Page 220. We're going to do 1B. All right? So stretch a little bit. Okay. Erase the board. Okay. And let's do a little ice. Ice is nice. Here we go. The equation I got N2, we know this one. I'm going to leave off the gas. N2 plus 3 H2s forms 2 NH3, an old friend, making ammonia. God love it. Okay, so we got ice. And the directions say just complete the table. Okay, so let's see. We're given this. we're given 5 moles and no moles, and we're given 2 moles at equilibrium and 1 mole at equilibrium. Okay, so remember how to do this? It's like adding or subtracting, isn't it? So away we go. Well, this is easy, right? We added 1, obviously. Well, if we added stuff here, then the other side we'll have to subtract, won't we? So let's see how much. Okay, if I added 1, well, it's 2 to 3. So I'll have to take away from the other side 3 halves times 1, or 1.5. And for this one, it's 2 to 1, so I need half of that, so I got to take away 0.5. But that means looking down, well, here we can subtract that now. 5 minus 1.5 is 3.5. And at the top, I got to go backwards. I end up with 2. I take away 0.5, so I must have started with 2.5. Ta-da! You don't have to solve it. You're done. That's all they wanted you to do for B. Okay? Let's do one that's a little more meaty. Let's go to, unless you got questions here. Let me see if you got questions. If not, we're going to go to number 5, so you can read that while I check and see if you got any questions. Okay, and I see you got, did we do all those? All right, I see you got more questions there. But you know what? I think I'm going to just pause here. I'll take your other questions on Thursday. Okay? So Aaron and Noah D, hold those questions. We'll take care of them on Thursday, along with everybody else's questions. But I think I want to do a little more ice here with you, just to kind of introduce this a bit. So let's do number 5 as well. So we're talking 221. Again, you can just do this right in your book with me. So number 5 says we got this stuff 3G3P, whatever that is, going to D half. And I'll leave out the A because I don't really care. And the K is 19. Am I being sloppy? Yeah, because I know what's important. I don't have to write KEQ. Okay. What's the concentration? What will the concentrations be at equilibrium if the initial concentration of each is 0.020? Let's do an ice like this, okay? So 0.020, 0.020. All right, well, for this one, you kind of got to look at the number, okay? Check this out, 19. So even though I'm starting with equal amounts of chemical, pardon me, 19 as a equilibrium number means it's bigger than 1, so it's going to go towards the products, right? So that means I'm going to make more products, and I'm going to take away from the reactants. But we don't know how much exactly. We're going to say X, but it's going to be the same amount because it's 1 to 1. That 3 doesn't mean anything. So it's going to be like this. So we got 0.020 minus X. We got 0.020 plus X. And we got K equals 19. Okay, time to do the equilibrium thing. Here we go. So the K expression from the equation is D HP over G P, but that's concentration of those puppies. And now we're going to put in the two things. So DHP was 0.020 plus x over 0.020 minus x. And that's all equal to the equilibrium constant. I should have written it there, equals 219. And you know what? From then on, it's all algebra. So let's do the algebra. So here we go. We got 19. We got 0.020 plus x equals 19 times this other big sucker, 0.020 minus x. It's kind of an unpleasant number. I'm going to put the book down so I can finish doing this. Okay. Whew. All right, so let's do some algebra. Can you see that? I hope I can. 0.20 plus x equals 19 times 0.2 would be what? 3.8, no, 0.38. I think. Is that right? 0.38 minus 19x. So I got 0. Check my math here, okay? Let me know if I screwed up. But I think that's right. Okay, so I got what? Point. We're going to subtract that from each side. So, no, let's not. Let's add this over. Let's get these guys positive. So let's get the x's over here. 20x equals 0.38 minus 0.02. So 0.36. So divide each side by 20. And my head's spinning, so I'm going to do that even though it's probably easy math here. So 0.36 divided by 20 is 0.018. And that's going to be moles, I think. But we're not done because it's an AP question. Now we got to actually read it and see what they want. Oh, they wanted the concentration at equilibrium. Oh, so we got to do like this. Ready? Here we go. Concentration of G3P equals 0.020 minus x. Well, it's 0.020 minus 0.018. So it's 0.002 moles or moles per liter, I forget. I think it was moles they gave us. And then the other one is going to be plus that. So it's going to be it's going to be DHP. So 0.020 plus x. Can we just do that in our head? So now it's going to be what? 0.018 plus 0.020 would be 0.038 moles. Which makes sense. It's 19, so I should get a lot of this stuff, 0.038, and not much left of the G3P stuff. So I think that's going to do it for you. Okay, so that's number 5 as an example. And let me just look at it and see how that went. And I'm wrong. Each of those wasn't moles, it was moles per liter. So pardon me. It's all molar, including this. Whoops, sorry, the number's right. So 0.018 moles per liter. My apologies. Okay, wrong label. Okay, how are we doing on time? We still got time for one more. So let's do one more. I had a bunch of them planned, but maybe I should just do one like this. Yeah, this is good. Let's go. Can we go to number 15, everybody? So page 224. Let's do 15. Okay, you may have to write a little small to fit it in there. So page 224. And we're doing 15. So that's it for this puppy. Again, we can just do it right in our books, as long as you can write small. If you can't, then do it on paper. Okay, so we got 15. Equal quantities of H2 and I2 are pumped into a flask. At equilibrium, the HI high is 1.0 molar. What was the initial H2? So let's get the equation, then we'll do an ice. So H2 plus I2 makes a couple of happy highs. And the K for that sucker is 4. With a number like 4, can you guess what we're going to have to do later? I bet you can. Ice. That was me. That wasn't your computer. Sorry about that. Okay, so here we go. Equal quantities of blah, blah, blah. Okay, at equilibrium, I got HI is 1. 1 molar. And I got equal quantities are pumped into this stuff of the H2. So let's just call it X and X. I assume I got none of that. So I'm going to add 1. Isn't that nice? See how that's working? And now look at this. It's 2 to 1. So if I'm making more of that, because it's 4, it's going to go forward a bit, isn't it? And I'm going to take away here. How much? Well, it's 2 to 1, so I got to take away 0.5. 0.5. I'll worry about sig figs at the end of the problem. So I got x minus 0.5. I got x minus 0.5. And my apologies. We should remember what we're trying to get, okay? It says, what was the initial concentration of H2? Which, of course, is x. So we really do want to find x, and that's actually our answer for this one, okay? Let's do it. So we got the equilibrium expression in letters. I got a couple of highs, HI squared, concentration of high squared, over H2 times I2. Remember, although it's plus in the equation, it's multiplied in the expression. I know you know that. And now let's do it. Okay, so we got 4 is our K, equals HI squared. Well, that's 1 squared. Well, that's a nice number, isn't it? Divided by x minus 0.5. Oh, but it's times another x minus 0.5, so I can just have that as squared. All right, what are we going to do to both sides of that sucker? Yeah, anytime they give you a nice square, you know you're going to have to take the square root. You just know it. So I got 2. I'm going to do the sig figs at the end of the problem. Equals 1 over x minus 0.5. And suddenly it's pretty easy algebra, isn't it? Isn't that a beautiful one? Don't you just love it? I know, I'm kind of sick. Okay, here we go. Let's do 2x. We're going to multiply this over. Minus 2 times 0.5 is 1. Equals 1. And I got 2x equals 2. Well, look at that. After that whole thing, x is 1 mole per liter. So 1 molar. Let's just verify that it makes sense. Okay, put in 1 there, minus 0.5 be 0.5. 1 minus 0.5, 0.5. Yeah, 0.5, 0.5. 1 over that, so 4. So 1 over 0.5 squared would be 4. So it checks too. It does make 4 if I put in 0.5, 0.5, and 1. So our answer makes sense. Okay? So I just wanted to show you an ice table that requires a square root. Huge. Okay, let's look at number 20 because it involves Q. All right? So number 20 on page 225. To get us thinking about Q a little bit. It looks hard, but I don't think it really is, in spite of all that wording, okay? So don't lose heart before we get started. Yes, it was a pun, but a really bad one. Kind of a rhyme. Okay, now, and I don't like this Cheryl thing she's doing with this big E. Just make a double arrows. So I got 2 SO2. It's all gases, so I'm going to skip the G. Plus O2 makes 2 SO3. I really don't get this thing of Sherry's. Really, that E thing. Don't worry about that. The K is 0.4. 0.14. At 625, we'll worry about the temperature if we need to. Okay, so reaction vessels filled, and it's a K. Oh, it's a KP, by the way. And remember, KP is pressure. We got to use pressure, so we got to use atmospheres. But we can do this because they give it to us this way anyway. So we're going to do ice and get this sucker ready. If a reaction vessel is filled with SO3 at a partial pressure of 0.1 and 0.2 atmospheres each of blah blah. Okay, so that's our initial. So we're going to do 0.1 and 0.20 each of the other two. 0.20 atmospheres, 0.20 atmospheres. We don't even need an ice table. Okay, is the reaction at equilibrium? And I got to say it's probably not. Look at the K, it's 0.14. Look at our K. So we're going to get Q. Remember, Q is just like K, but it's not at equilibrium. So we're going to do SO, the pressure of SO3 right here, but that's squared, divided by the pressure of SO2 squared times the pressure of O2. So chuck in the numbers here. All right, here we go. So we got 0.2 squared. I got 0.1 squared times 0.2. Okay, so I got essentially the 0.2's cancel out partially, so I got 0.2 over 0.01. Well, gee, the Christmas kids, let's just do that. So that's Q. So I got 0.2 divided by 0.01 equals 20. It's not a zero, it's a Q. So Q is 20. Look at that, that's really big. What's it supposed to be? The QP is supposed to be 4.14, so it is definitely too far towards which side? Starts with a P. So too far towards, see, it's too big compared to what it should be, towards the products. So it's definitely not at equilibrium, just to say that answer. Let's look at the problem and answer the question now. Okay. Okay. Is it at equilibrium? No, it's not at equilibrium. If not, which direction will it proceed to reach equilibrium? Well, which way's it got to go, folks? It's got to go, it's too far towards the reactant, so it must go towards the product, sorry, it's too far towards the product, so we got to go towards the reactants. Ta-da! Finished 20. Our time is up. Thanks for waiting the extra minute. Enjoy the rest of your day. We'll answer the rest of your questions Thursday. And thank you for joining me. Yeah, we'll see you Thursday. Goodbye, gang. I'll save this on the AP Classroom if you need to refer to it. Okay? Toodaloo.